Hey guys, and welcome back to another YouTube video. This is gonna be the second part of our optimization and neural networks from scratch video. In this video, we're gonna be talking about some various advanced optimizers, and we're gonna look at how they work and how they are really just add-ons to your previous optimizers. So in this video, we're gonna be looking at something like RMS Prop, grad, and some other optimizers that you might be using in your like daily neural network tasks. So without further ado, let's get right into it. All right, so now, as I told you in my first video, I have this PDF that I had created, and I also have the link to the GitHub repository in my like description, video description, so you guys can go ahead and check that out, because this is how I am gonna be teaching it. It's gonna be like a lecture note teaching style. So I think we had covered like everything up till momentum. I hadn't covered Nestro's accelerated gradient. However, it is extremely similar to that stuff. We just had an extra uh, beta m term to this, and that will allow you to do something basically further move in the direction of the gradient. And I won't exactly go explaining that, and I'll kind of leave it as an exercise for you guys. And I have explained it over here, so you can go ahead and read this. If you don't understand, comment down below and I'll kind of explain it to you. So the first optimizer that we're going to be looking at today is going to be adaptive gradient descent, or ADGRAD for short. Now, I don't know if you have ever used ADGRAD before, or if you have heard of that name. I'm pretty sure you would have heard of the name ADGRAD because it's a pretty popular optimization technique. Now, I know that these days people usually just like to use RMS Prop, and Adam. However, these types of optimizers were some things that people used before we had RMS Prop. So it's important to understand how these work, because the way RMS Prop and all of your better optimizers work is by improving on the issues that you would get when you use something like Adgrad. So, alright, let's go ahead and understand this. So, the first thing is, why exactly are we calling it adaptive gradient descent? That's something that you should kind of understand, because if you understand the name of the activation optimizer, you will actually understand kind of sort of what we are trying to achieve through this optimizer. Now, when you say adaptive gradient descent, we mean that the learning rate of your gradient descent is scaled adaptively. Now, I know that's kind of a vague explanation. Let me explain it to you again. So, when we are doing like your standard gradient descent, what we are trying to do is we are trying to converge to a minimum on the graph. So, if this will be your JT, this will be your loss, then we are trying to find a minima to your loss. So, in this case, an optimal situation would be this, but we might just end up here or here. This would be an optimal situation. Now, if we start over here, the optimal situation is probably going to be this one. Now, in this case, we obviously always specify the learning rate. Now, the learning rate is obviously the size of the step. Now, the thing is, if we say that the learning rate is, let's just say, 10 to the power of negative 4, like in a way, yeah, all right, that's a good learning rate. However, we kind of can just judge by common sense, is that let's just say a blob isn't even here, it's over here, we are over here. Now, when we are over here, we don't really care to step just by this amount. We want to step a lot, and we only want to step small. We only want to have smaller and smaller steps when we are converging to a minimum. So in that case, we shouldn't be having like a constant learning rate. We should have a learning rate that varies, and that's exactly what Adagrad wants us to achieve. Is that we want to have a learning rate which we can which can vary according to the position and the loss that you are having at that point in time. So yeah, that's basically what Adagrad does. And I know it sounds not that complicated, and to be honest, it really isn't. And if in your case it sounds a little complicated, then you can just go ahead and look at my gradient descent video, because if you see that, you will see that it's actually not so complicated, and these pretty long and complex looking equations are actually very simple. So I'm not gonna be explaining you what gradients are and stuff like that this time. I will kind of be assuming that you know all of that. So first we are gonna be looking at equation 2.6 because that's like the first equation. Because the second equation is a parameter update equation, and in this basically where we use this as parameter that we calculated to update the theta parameter. So the first thing is we need to calculate the s parameter. So the way we calculate it is the S new. So you can kind of look at it as the S new is going to be equal to the S old minus the eta uh, nabla theta j theta, and we have a now see. All right. So the way we look at this. Oh, okay. Why was I copying the update equation? I'm so sorry. So what we are doing here is something really cool. Now, can you see this? Now this is basically over here also before I say this stands for element wise multiplication. So you take every element of the first matrix, which is going to be nabla theta g theta, and then you take every element of the second matrix and you just multiply the total. Okay? So that's what this stands for. So we are not doing anything like tensor products or anything like that. This is element wise multiplication. So yeah, and I have just given it right here in the above equation. This represents element wise multiplications. Keep that in mind. All right, so all right, so we are basically we scale down the gradient vector down its steepest dimensions. That's exactly what I was trying to explain to you through this graph that we had just drawn. We want to scale down the gradient vector to the steepest dimensions. So here, as you can see, what we are doing is we are taking the gradient and then we are effectively just squaring the gradient. So basically what this does is that if the cost function is getting steeper along some dimension, n dimension, k dimension, whatever it is, then we want that, okay, what is happening over here? Okay, yeah. So if the cost function is getting steeper along the kth dimension, then the value of s will also get steeper along the dimension. And we can effectively get that by squaring of the gradients. Now in this case you will see that it's like there are still going to be issues with this, but yeah, the main issue that you kind of get with Adagrad and this equation over here is the fact that it pays equal attention to all your iterations, like all your the entire kind of iterations, all of your iterations. However, that kind of sort of leads to certain issues, which you will see when you apply neural networks practically. So, keeping those issues aside, let's move on. Now, the update equation is again a very simple equation. If you go ahead and look at this, this is just you performing gradient descent. This is just a gradient descent. However, the entire adaptive part comes in when you are doing element wise division. You take an epsilon term and you add s. Epsilon term is really just something of a soothing factor. Uh, Basically, what it means is that you don't want division by 0, and there are going to be certain cases where s becomes 0, and well, root of 0 will be 0, so that will give you x upon 0, and you can't have that because then your theta will just go crazy. So that's why we had a little epsilon term. Epsilon terms are very very small. They're gonna be like 10 to the negative 6, 10 to the negative 7. So because you don't want your s term to get influenced by the epsilon term. However, if your s term is 0, then you do want to have an epsilon term. So that's the only reason why we have this. There's no other reason for this one. Alright, so we have our s term over here. So this will basically show how you want to affect theta. So that means if you based on like if the value of s plus epsilon will be super large, then theta will become small. So the size of your learning rates get smaller, and that's really what Adagrad is trying to achieve. Now, that's exactly what we have summarized over here. It is used to decay the learning rate adaptively. That is more during the larger slopes and less during the smaller slopes. And yeah, so all right, you can go ahead and read this if you kind of want. So the next thing that we want to look at is RMS prop. Now RMS prop is really just add a grad, but we kind of add some extra stuff to it, and just so that we can make RMS prop a little better. I'm sorry, make add a grad a little better. So when I was explaining you add a grad, I kind of hinted at the one issue that it just looks at the gradients of, it looks at all the gradients of all the iterations, which does not work out very well in a lot of cases. Well, RMS prop is really just created to fix that problem that we had looked at. So what it does is it pays extreme attention to the recent gradients. Now that's a really cool thing. So if we know that we are converging, we don't want to look at information over here. We want to just look at stuff that's happening over here if we are present over here. And that's exactly what RMS prop does. So this is what we can get when we use something like RMS prop, and this is what we would get if we were using something like Adagrad. I know my handwriting isn't the best, but there we go. So Adagrad has a risk of slowing down too fast and not converging to a global minimum. And that's something that does happen a lot. And that's the kind of the problem that I was talking about, is that you will see that your losses, they will go down, but what's going to end up happening is uh, it will kind of plateau at a point, and it won't get below that, and it will be very easy to go below that if you just choose a different optimizer, which is going to be RMS Pro. So the way you will choose an optimizer in your neural network is, let's say you first use something like Adagraph, just experiment it, and you will see that you will have like a plateauing loss. So let's say if you're when you actually plot your epochs with your loss function, you notice something like this. So if you have your L theta loss function over here, and then you have your epochs, you will, let's say if it's something like this happens, where you do that and then it kind of plateaus out, and let's say that this plateau value is something like a point 4. Now that's not a very good loss, right? Because you want to minimize your loss. So in this case, let we are using Adagrad, right? So what you would say is that, all right, well, that means that we are converging to a local minima that's not that optimal. So if we can converge to a minima that has a point below point 4, then we will be able to achieve a better lower loss. So that is a better model. So in that case, you would go ahead and use something like RMS prop. So that should, which will fix that problem that we are having, and now you probably will end up with maybe a point 1, point 0.05, something like that. And this is really why, this is really how you would go ahead and choose your optimizers. And this is why I always say it is important to learn the math, because if you didn't know the math, and you wouldn't know the correlation between Adagrad and RMS prop, and you wouldn't know that RMS prop is really just an improvement on Adagrad, because if even if you look at the equations, they are highly similar equations. In fact, the update equations for RMS prop and Adagrad are literally the same equations. They are the same equations. It's the only extra beta term in each of these which makes RMS prop a little different. Apart from that, it's literally the same as Adagrad. And that's the reason why it is highly important that you understand the math and not just what an optimizer is using like theoretically. So Adagrad is, again, I will repeat what I just said. Adagrad has the risk of slowing down too much and not converging to a global minimum. RMS Prop tries to get rid of this issue by accumulating gradients from the most recent iterations rather than all of the gradients from the start of the training. This is done by introducing exponential decay in the first step, as given as seen below by the hyperparameter beta. So this basically exponentially decays your gradients and stuff. Not, I'm pretty sure it decays your learning rate, and in this way you will basically pay more attention to recent gradients and not past gradients. So basically, the way this works is we add this beta term. So if we set it to zero point 0.9 or something like that, you will see that the factor s will obviously get scaled down a bit. And then when we perform this entire equation, this entire thing will also get scaled down to 10% the original value, because it's zero point 0.9. So no, sorry, it will be 90% of the, no, it will be 10%, because we are subtracting it from 1, right? So it will be 10% of the original value, and as you can see that that kind of decays. So the value of s that you will obtain will be much smaller, and therefore that will kind of work a little better. which, and this is the issue that Adagrad was having, because in this case S could get very very large, and then that would kind of mess up, because the value of theta would become super small, and you don't want that to happen. So in this case, by adding a zero point 0.9 hyperparameter, you are effectively reducing the size of S, and therefore you are kind of it's kind of adds like a little bit of, an analogy for this would be that it kind of adds a little bit of friction to it. uh, no, I don't think that's the best analogy, but basically what I mean is that the value of S, it gets smaller and smaller a little slowly. Actually no, it gets larger and larger a little slowly, and so the value of theta, it will only get small when you need it to get small, and it won't get super small very fast, effectively making your model converge at a minimum that you don't want it to. So that's really what Adagrad and RMS Prop do. Now you will see that Adam is really just, you take Adagrad, you take RMS Prop, and then you kind of mush them together in a way, and that gives you Adam. Now, Adam is a pretty complicated optimizer, because as you can see, it takes up a bunch of equations. Now, these two equations you really don't need to worry about, because to be honest, even the books that I was reading that dealt with Adam, they were all like, just don't worry about these two equations, because you are just kind of, there are certain issues like numeric, mathematical issues that you would get when you simply run these two equations and you put them in here, and so you all you do is you just implement these things in there, so you don't get those issues showing up. So that's really just what you do. And now I want you to look at this stuff a little carefully. What you will see is that this is just RMS prop, right? This is literally RMS prop, right? So, and that's exactly what we say is we combine momentum and RMS prop. I'm sorry I said Adagrad before, because this is momentum right here. So as you can see, we are basically, and also I'm pretty sure this has to be an M and not an S. I think that's just a typo over here. I just noticed that. So over here, as you can see, this is just your RMS prop. And then if you add a little bit of momentum to it, which will smooth out all of your gradients, which was something that we saw in momentum, and also increase your processing time. And then you have the values of M and S. And so in this way, what you can do is, initially what we were doing is we were having our uh, uh, grad j theta over here. However, in this case, what we can just have is m hat, which will encompass the this entire equation. So that encompasses the grad that we wanted, and then we can just multiply it by the learning rate and divide, do element-wise division using the RMS prop optimizer, which is synonymous to what we were doing over here. Very similar. So that's basically what Adam does. So as you can see over here, now I have a bunch of things. Momentum decay parameter is m1. It's gonna be zero point 0.9, which is something that we had talked about when we were doing momentum. And the scale decay parameter beta 2 is initialized to 0.99 in a normal case. You can actually do that when you are going to be defining your optimizers. If you go ahead and actually create the object first, you will be able to set these parameters. So yeah, that's pretty cool. NADM, I won't go over NADM, because NADM is Adam plus Nestor's accelerated gradient. And since I haven't explained what Nestor's accelerated gradient is, I want you guys to figure out what it is, and then comment down below. And if I get the correct answer, then I will make another video where I'll show you what NADM really is. Because it's very similar to Adam. Really, all you're gonna do is you can just add another term in this theta with theta, and that's going to give you NADM. So that's really what it is. So as you can see, pretty simple. Now as you can see, I'm still working on this, and as you can see, there are so many things that you still have to cover. And in the next video, I'm planning to go over stuff like the vanishing and the exploding gradient problem. One cool thing about these is that we are not going to be having any math, but if you do like math, then I'm sorry, it's not going to be very cool for you. But yeah, it's gonna be a good video. If you want, I would highly recommend that you go ahead and read this. Basically, because the entire thing is kind of basic. I mean, it's not too crazy. The vanishing gradient problem is pretty basic. So you can go ahead and have a read at it. And if you understand it, then that's awesome. If you don't, then I'm gonna have a video on it. So yeah. So I hope you enjoyed this video. If you did, like, subscribe, comment down below. And now I'm just gonna go ahead and give you a quick revision on what this is. So basically, when I say quick revision, all we can do is we can look at gradient descent. Gradient, it's the direction of steepest ascent. So if you want to do direction of steepest descent, you take the negative gradient of anything. So we just take a j theta, take the negative gradient, and then we have obviously your theta parameter from which we will subtract it, and that gives you the value of theta. But we are again getting an issue. We have to actually step down, so we need to have a step size. So we finally end up with the equation, this one. So this is going to be your equation 1, but you obviously have to update your theta parameters. So you take that. So in this case, since the theta parameters are getting updated by itself, so that's good. But I mean, again, so now we can go ahead and actually do that. So if we do something like grad theta msc, that gives you a, I don't know, is this a row vector or a column vector? I forgot that. I always mess up rows and columns, so that's why. That should be equal to del theta 0 msc of theta. Then it should be del theta 1 msc of theta, del actually it will then just be some stuff, and the generalized equation will be del by del theta n msc theta, which will end up giving you 2 over m x transpose x theta. You can work this out numerically. The reason why we don't do this is because it is batch gradient descent. It takes the entire batch. We want to divide stuff into mini batches, then do stuff, or we kind of want to speed it up using something like momentum, which we have right here. Momentum can further be uh, made more accurate by using energy. This is your exercise. Then we learned that learning rate is a pretty important thing. So we should know when to scale up the learning rate, when to scale down the learning rate, how to do that. And for that, we used Adagrad. This is the equation right here. And then we updated using this equation right here. That is pretty neat. Then we learned that Adagrad has its own issues because it looks at all the iterations. We don't want that. So then we introduced our decay parameters, beta, I'm sorry for that, and then we created RMS Prop. And then we just said, well, what if we take RMS Prop and RMS Prop and momentum and fuse them into one, and that gives you, drumroll please, Adam. And there we go. So that's basically it for this video. Now I think this video wasn't that long, to be honest. I mean, what was the duration? Yeah, oh, 23 minutes. I don't know, time flies. So whatever, this video was a little long, but that's okay. I hope that you understood what it was that I was trying to explain to you. This is one of the first mathematical videos that I've ever posted. Like, not the first, it's like the second or the third. But it really gets a little difficult for me to explain these kind of advanced concepts. The main reason being, uh, I simply, I'm okay. I think I'm good at explaining programming, but I don't know if I'm good at explaining like technical concepts like math. So I would highly recommend that some of you, you comment down below and let me know if I did a good job, or if you wanted some sort of a different explanation with some more analogies and stuff. Because the way I learned this is I read through a book, and to be honest, I that's like it gets me a different feeling, and to read a book and understand. So that's why I even wrote this stuff out so you guys could understand this a lot better. These are really just the notes that I was taking when I was reading that book. And I'm gonna create a GitHub repository for you guys containing all the code that I write for neural networks, basically because I am currently working on a bunch of advanced projects using neural networks. So you can go ahead and access all of that GitHub repositories over here. So yeah, that's gonna be super cool. And besides that, I would highly recommend if you try to learn this stuff by yourself. Yeah, I have created a bunch of other chapters, so it's not just layers for CNNs. Now I've created RNNs, LSTMs, and GRUs, and I am on attention mechanisms right now. I'm creating the chapter for attention mechanisms, so you guys can definitely check that out if you want. So I'll probably post the updated version directly in the. I can just kind of commit it to GitHub, and you guys can go ahead and access it. I don't know if I will. I think I will also provide you the link in this video description for the GitHub repository. So yeah, that is it for this video. I hope you enjoyed it. If you did, like, subscribe, comment down below, and yeah, please comment down below with the answer to my exercise for the NAG. And